Okay.
Thank you.
All right, well, thank you for the introduction. So I will be continuing this series on the basics of Fermion quantum Monte Carlo. Today I'll be focusing on the projective algorithm, which for some of your projects you may have even seen already, depending on which tutorials you've looked at this point. And then I'll also talk about the models that are sort of built into ALF that you can use or you can choose to work with and modify yourself. As before, I'm getting a lot of this content from the documentation as well as the textbook on the QMC methods. Okay. So to remind ourselves where we were talking about the Hamiltonians, where we could split things into a kinetic piece or a bilinear piece, and then sums of squares of Hermitian operators. And so the point of doing that was so that we could, after we trotterize, do a Hubbard-Stratanovich transformation and be able to write things in terms of these auxiliary fields L. And these fields, as we discussed, well, sort of the default value that we use with the model are these L equals +1, ±1, and ±2. So for these four fields, and it turns out that this is actually a type 2 field in the code. So I wanted to mention this before going further, that there are actually a few different options one has for these fields, both in terms of auxiliary fields and in terms of physical fields. So we have four types of field options currently, and they're stored in this F value, which could be complex and is complex in general. So I think I had a question about this yesterday. The first type is actually for an Ising field, where this field value, it's completely real, but the real part is just ±1, which is stored. And this would be used for some of the Hamiltonians, which I didn't discuss in detail yesterday, but also involve spins that interact with fermions. So we have a class of Hamiltonians that have those, and so they use this type 1. And so the type 1 fields as currently implemented are for physical fields rather than the Hubbard-Stratanovich. Okay, and then type 2, as I mentioned before, this is the one that we're familiar with these four values of ±1, ±2. And then we have two additional types. We have type 3, which are for continuous fields. So one can also do the continuous Hubbard-Stratanovich transformation. When we get to the Mol Hamiltonian families, I'll mention that, but there's a toggle you can do for continuous or not, which will allow you to use these continuous fields instead. And then finally, this is new to ALF of this year, this type 4, where this is the only one right now where we use both the real and the real and imaginary parts of a complex field F. And the idea here is we actually have one Hubbard-Stratanovich field of like a type 2 type of field, which is stored both in the exponent, depending on ±1, ±2, that changes this eta, as well as the prefactor, just as we would see for the type 2 fields. But then the imaginary part of F is continuous, and it's actually for, it's continuous. It's actually for simulating terms that look like this, where we have a spin that is coupled to a fermionic operator, but it's a squared one. So it's a quartic type of term where one would need the Hubbard-Stratanovich field in addition to this physical field as well. And so this is a new type that one can use for the spin spirals, which I'll talk about later. Okay. So with that in mind, let's move on to the projective QMC version of Fermion auxiliary field Monte Carlo. So yesterday, when we were talking about how to get to zero temperature physics, we were looking at the partition function and taking the trace of e to the minus beta h, where beta is the inverse temperature. If we are only interested in the zero temperature physics, because often when we do that, we're still interested in that. We do finite size scaling, we scale beta. But if we are only interested in zero temperature and nothing finite temperature, an option is the projective algorithm, where what you do is you introduce a trial wave function, which I'll talk about in a moment. And the idea basically is that as long as the trial wave function has overlap with the actual ground state that you want, you can then do the imaginary time evolution e to the minus theta h. As theta goes to infinity, we will go down, we will get the ground state ultimately. And so all of these higher energy states will disappear. And so the only thing left is the piece, is the ground state we project into it. And then we also, for the algorithm, so we can still do time displaced correlation functions and whatnot, we do have a beta, e to the minus beta portion inside here as well. And so the trial wave functions in the code are Slater determinants. And what you can do is take a non-interacting problem. So you could take some of the, say, the hopping term in your Hamiltonian and get the exact ground state of that. And that is one candidate you can do for these trial wave functions. And this is an example actually from the documentation for the half-filled Hubbard model, comparing the PQMC, so this is the projector, versus the finite temperature QMC algorithm for basically the equivalent amount of imaginary time evolution. And one can see that the black data is the t equals 0 algorithm. So you can reach the zero temperature physics faster, basically, with less of this theta than what you would need for finite temperature. So that's something that's nice about it. If we're thinking about when we would want to use it in pros and cons, well, main one is it can converge to the zero temperature physics more quickly. Another nice thing is, we are coming up with a trial wave function. So one might think, oh, is this like a variational method where I truly have to know a lot about the ground state? But you don't in this case. All you need is an overlap with the ground state. So you don't have to know that much about the ground state in order to use this. And then Johannes may talk about this tomorrow with stabilization, but there are some stabilization advantages to the projective algorithm as well. The cons are, well, you don't get finite temperature physics. And then also you need to choose a good trial wave function. If you choose something that doesn't overlap with the ground state, then you just absolutely cannot get the ground state, for example. And then also, this is another piece that can potentially introduce a sign problem to your model as well. So this is sort of, a piece of the model building if you decide to go the projective route. Okay, so let's talk a little bit about the trial wave function and then the resulting weights if we're doing a QMC with this. So the trial wave function, like I said, if we think about taking the t part of our Hamiltonian, that's an option. And if we're assuming a half-filled system, then one thing you could do is you could take all the single particle solutions of this, and you can multiply by half the total number of possible particles one could have to get a half-filled solution. And use this as your trial wave function. But we can think in general of a product of these operators. And so if we're thinking in terms of the matrix, the unitary matrix that would diagonalize the Hamiltonian, you could then write it in terms of your lattice operators for the sites. And then we can think of the wave function then in this form. We get this P matrix. And so then this P matrix ends up being part of our code as well. It'll enter into the calculation. And so then when we are looking at the weights, the weights that we're going to have are going to come from, I should have made, I just realized I made this yesterday, that this should be more specific to the configuration. If we think of this as for a particular configuration phi, then this is going to be equal to the determinant of these matrices times the P matrices from the projection, or sorry, from the Slater determinant. And I'm going to show a little bit about how you can see that. So if we go ahead and write down our trial wave function in terms of this P matrix. And then we think about what this looks like. This is like a product of NP sums of up to n particles, where that's the number of particles in our site well, that's n is the number of sites or yeah, possible particles. And so it would be something like if we're thinking about the types of terms that appear in this product, I'm just going to write a few out simply just so that we can see what this would look like. We have C1, P11 plus C2, P21 plus C3 dagger, P31. So that would be one of these terms in the product. Then, you know, we have C1, P12 plus C2, P22 plus C3, P32. And when we think about the things that are multiplied overall, because we would multiply. Oh, okay, I'm going to move to the next step. Because what we want to do in order to get a formula like this is see what the overlap is for two of these Slater determinant type of functions. So for this, what I'm thinking about is a P dagger multiplied by Cn, and then another product with n prime, and then a C dagger P n prime. So from this side, we're going to get terms that look like this in the product. This side, we're going to get the terms that, you know, look somewhat like that. And the point is that for each of these terms, they will have one contribution from, for example, with these P's, a 1, a 2, a 3, a 4 for the second index. But for the first index, they could have any combination possible for the first index, because any of these are where, in fact, we get all combinations possible, any of these multiplying any of these. And so if we write this out generally, what we're going to get is a sum over various combinations of the y indices. And then we're going to have the P daggers going from NP down to 1. But this index is going to vary among all possible numbers, while this has 1 through NP. And then for the P's, we're going to have y bar 1 to y bar NP. NP. So for these, this first index can be combined with any of the other ones. But then the second index, there's going to be exactly one of each from 1 to NP. And so then the matrix element is going to involve C dagger NP, C dagger YNP to CY1, C dagger Y bar 1, up to C dagger Y bar NP. Okay, so if we have a set of operators like this, what do we need in order to get non-zeros for this matrix element? Just assuming these y's are anything, what type of limitations would you get for the y's?
Why bars are the permutation of whatever?
Yeah, exactly.
So I'm gonna repeat my answer to that. The y and y bars need to be a permutation of each other.
Yeah, the first more simplistic thing you could say is first that if we look at all these y, let's just think of y bars. First, they must be all different. Because if we had two C dagger ones here, then that would give us a 0 at that point. We can't have more than one. But then more than that, we have to match these all up with each other in some way. Yes. So we have to, whatever we created on this side, we have to annihilate on that side. So yes, what we then have is that the y bar, I'll just write it in this way, is some permutation of the y's if we're thinking about the set of them. And then moreover, from there, we get that this matrix element will just give us the sign of the permutation that I've written here.
Switch to another color because somehow
Oh, the black is not showing up.
It's chopped up somehow. So.
Oh, okay.
Maybe try a few ones, just some line.
I mean, it's worth a try.
Okay, so try, yeah.
Try different colors.
Okay. So just thinking about this more broadly, we have these matrices. They're these matrix elements, that is, they're multiplied together, and then the y's and the y bars, we get 0 unless one is a permutation of the other, and then this matrix element gives us the sign of the permutation. And so I wasn't going to talk too much more about this anyway, because there are some details that you can again get from the textbook that I've mentioned. But ultimately what you get is you have a sum of the possible permutations for these NP particles, and then you have the sign of the permutation times P dagger, the matrices P dagger P, 1 with the permutation 1 to P dagger P up to the NP times the permutation of NP. And this is just the definition of the determinant of P dagger P. So the first point here then is that an overlap of these two Slater determinants is just going to be the determinant of P dagger P. And then the second formula, which I'm just going to list, but is important in order to understand this piece, is that if we have E times C dagger TC times the product from n equals 1 to NP of C dagger P, just that state. That's equal to the product, but you can put the matrix inside. So we have the matrix E to the T times the matrix P. So these two relations together are what allow you to then just write this as a product of all of your bilinear pieces. And it's important, what I said here isn't really correct. It's important to have the bilinear pieces in there so you can use this formula. Okay, so that's the weights. And then for the projector algorithm, one can compute and define the Green's functions again, both time displaced and equal time. They are in a different form compared to finite temperature. So the Green's function for the projector algorithm is this 1 minus, and then we have a product of the B matrices times the P matrix for the right side, because you can do different trial wave functions for the right and the left. And then we have a product of all the matrices that we're taking the inverse of, and these are in the order from the right over to the left. And then we put the rest of them for tau greater than the tau of interest on the right here. And so this all together is a square matrix, but it's important to note these pieces on this side and that side are actually rectangular matrices. And then this Green's function for the projector QMC, it really is a projector. When you square it, you get the same Green's function. And then the next nice thing is that the updates end up being in the exact same form as what one sees for finite temperature, quantum Monte Carlo. So the calculation of the Green's function is different, but then all the other pieces around it end up being the same. So for updates, you just use this projector Green's function the same way you would do with the finite temperature. And I'll briefly show basically the equivalent of what Johannes showed yesterday for a ratio of two determinants, that you get the same thing. Do we have an eraser? Oh, there we go. So to write in a compact form, if we have the B matrix for configuration phi times 0 times P, I'm going to call that the B matrix for the right side. And then P transpose, then the B matrix for the rest of it, let's say 2 theta plus beta tau. This would be the B matrix for the left side. And then the Green's function using these for equal time is going to be 1 minus BR times BL at phi, BR at phi, inverse BL for phi. And so what we want is the weight ratio. So I'm just going to write, we've got our omega with phi prime, where I'm assuming, like the Hubbard model, that there's a one spin flip of difference. It's fine. It just wants to be up, basically. Oh, the wind makes it? So using the notation that Johannes used yesterday for the finite temperature, we can just write this as the determinant of the one with the 1 plus delta, where delta is a very small, well, it's a very sparse matrix. In fact, for a single spin flip, it's going to be the same, it's going to be 0 everywhere except for one diagonal entry. And so with the ratio of two determinants, we can write this as the determinant of this numerator and then we can put this, the piece in the denominator up as an inverse, because this, as a note, this is a square matrix here, because we have the dimensions on either side are going to be this NP. So BL, BR phi inverse. And then when we do this, we would be multiplying these two, but we've got this one times its inverse. And so what you get is the determinant of just 1 plus, and then there's this delta times these other matrices times this B on the left. But when you have 1 plus AB, even for rectangular matrices, you can say that's equal to the determinant of 1 plus BA. So using that identity, we can write this as 1 plus delta BR phi times our BL times our BR phi again, inverse BL phi. And then this, we can remind ourselves of the definition up here of what the Green's function is. So we end up simply getting the same expression for the finite temperature, where we have 1 plus delta times 1 minus G of the original phi configuration. So with this weight ratio, we can write this in terms of the equal time Green's function, again, for the updates. So just as before, the equal time Green's function is going to be the central quantity. We use it to build the observables in just the same way. And then we can also use it, perhaps more surprisingly, for the updates in just the same way, the same formulas. Oh, I went the wrong way. Okay. So from here, I was going to give an overview of the example Hamiltonians, or really the Hamiltonian classes that are part of the ALF code. And so all of these you can just work with out of the box, and they have the, I'll talk about the parameters involved for them. But also, if you want to build your own model, which I think there will be some discussion of tomorrow, you can use these Hamiltonians as a base, and so it's useful to know what's available. Okay, and this slide is just a few of the different systems that have been studied with ALF over the years. I have not included most of the most recent applications, but one of the nice things about this list is most of the things on it are either currently supported Hamiltonians or semi-supported Hamiltonians, which I'll mention. But yeah, condo systems, gross niveau, pneumatic critical points, lattice gauge theories, long-range Coulomb interactions, SUN quantum antiferromagnets, and so on. Okay, so this is the general ALF Hamiltonian that we currently have. And so based on what we've learned so far this week, it should make somewhat sense why these are the types of terms that we have. But we've got the fermionic bilinear, or the hopping terms, as this HT. And then we can have, for interaction vertices, we're going to have squares, and they're going to be bilinears, plus we can add whatever constant here. That's this alpha. Somebody trying to get in. And then we have an interaction term, well, this HI, and this is, again, for if you want actually to have quantum spins interacting with fermionic bilinears. And then this HQ is the latest part of the Hamiltonian functionality we've added, which allows you to have a bosonic term, this 1 plus Q, but it's coupled to quadratic term squared for the fermions. So yeah, this is the new one, the spin pyrals term. Okay, so then let's think about a bit from that, huge Hamiltonian, how we would actually implement some of these things. Now, I'm going to first talk about the SUN Hubbard models, which are already in the Hamiltonian classes, but I think it's useful to think about how we would identify the different pieces in that large Hamiltonian. So these are the two relevant pieces that we would want to work with for the Hubbard model. And we know it has this on-site interaction, and this is specifically in the density channel that we're looking at for how we write it as a square. And so on a square lattice, our lattice vectors are going to be 1, 0, and 0, 1. And then these are all variables that one would set internally. If some of them you can set from parameter file, but others are internal for if you were creating your own Hamiltonian. So ndim is going to be the number of lattice sites for this. Now we have the concept of flavors versus colors. So the colors, you can see, are all identical. This is the NSUN in the code because each one of these is going to be basically another copy. And this is why a lot of the models are SUN models in general. And so if we're thinking about the SUN Hubbard model in particular, that's what this sigma is. And the number of colors is just going to be the N in the SUN symmetry. The number of flavors, on the other hand, that's this S index. And you can see that you can have different interaction pieces depending on what your S value is. So the flavors themselves are different. So in the case of this decomposition, all of these are identical, so number of flavors is set to 1 here. The MT, oh yeah, so MT is the number of types of T matrices we have in the kinetic piece, so that's equal to 1 here for the nearest neighbor hopping. And then UK, to get this to work for the NSUN, when we write this as squares, it's U over N. MV, which is the number, this is an on-site interaction. And so we're going to have as many interactions as there are lattice sites for the Hubbard model. And then this V potential term, well, it's an on-site interaction. So it's going to be set so that we both for IJ, they're both going to go to the same point, K. And then we can set this alpha KS. This alpha KS is actually within this. This is actually, within this N color sum. So it's going to be equal to 1/2 so that we get 2 of them, or maybe minus 1/2 actually. Okay, And so that's how you would think through these components if you're making the model. Now, for like I said, if you actually want to do the SUN Hubbard model, and in particular the density coupling I just mentioned, this is already a model class you have. And so these are the variables available for the Hubbard model as it is. And so this, if you want it to be the density channel where you have both, where you have the, both of the flavors have the same sign in here, or both of the colors have the same, you have colors, then you would set MZ to be false here. And then you have T for the hopping, a chemical potential, and the interaction. And then we also have the bilayer version available too. So you can have hopping on the second layer, the on-site interaction for the second layer, and then hopping between the layers too. And then this last parameter is this continuous field variable that I mentioned before. You can use continuous fields in your Hubbard-Stratonovich instead. And so that's a feature of the ALF, but you're studying still the same model. Okay, on the other hand, we can also do the MZ decomposition for the Hubbard model. And so to think about the distinction of this model or this way of decomposing versus the last, now we have the spin up minus the spin down in the square. And so the result is most of this stuff is the same, but the flavor, the number of flavors that we have is going to be 2 since these are treated differently. And then the number of colors is just 1 if we're looking at the Hubbard model. But this is part of a larger class of these MZ Hubbard models, which are the same for 2, as I showed you, when we have 2 types of fermions, spin up and spin down, but actually beyond that are different classes overall. But again, these are the parameters available. The one thing to keep in mind that's a little different from in how it's written in the general Hamiltonian when this is implemented is when you give the number of colors NSUN, it's not listed here, but the way this model is defined is actually from sigma equals 1 to NSUN over 2. So if you want to get the Hubbard model, you put NSUN equals 2 here, it'll turn it into a 1 there, and then you put 2 flavors in as well. So this is something that might be a little confusing about this one in particular. But this, and so this model is defined only for NSUN even, but all of this is also written as a comment here. Okay, and then beyond that, we had the Hubbard models with the on-site interaction. There's a whole class of SUN TV models for nearest neighbor interactions. And, we've got the hopping, chemical potential, and so this is something you could build off of as well or work with for the TV. And it also works for bilayer systems. And then beyond that, we also have supported the Kondo SUN models, where we have basically fermionic bosonic interactions, but the bosonic ones are fermionized. So we have 2 types of fermions in the Hamiltonian. And so then you can read a lot more about this in the documentation if you're interested. But this is again to show how the squares aren't really that limiting, because you can decompose even complicated things in terms of squares to get what you would like. And so then, and so you can look in the documentation, it gives you the parameters and parts for studying it. We have long-range interaction models. So this is instead of nearest neighbor only, if you want a V that will decay, basically, as you get further and further apart between sites in the interaction. And there's some variables worth reading about. One is about how the Coulomb tail magnitude, this ham alpha, which is different from some of the other models. And then this percent change is actually related to the algorithm and acceptance ratios. So this is something you can play with this model. And then finally, well, not quite finally, we have the Z2 gauge series coupled to matter. Lots of options here for spins that live on bonds, but also we can have spins that live on sites. And these will all couple to either spins by themselves or coupling to fermionic bilinear pieces. And then this is the newest class, this spin pyrals model, which is specifically for SU2, the square lattice. And this is the one where you can have spin degrees of freedom, or sorry, bosonic degrees of freedom. This is continuous interacting with fermionic squares. So yeah, as a summary, we have these supported Hamiltonian families. For these first four, the Hubbard models, TV models, Kondo models, long-range interaction models, the code supports all 5 of these lattices that Johannes mentioned yesterday. And then also the symmetric Trotter decomposition is an option for all of them. And we have projector form as an option. And then, I mean, projectors available for both of them, for all of these, I guess. I guess I was just noting that. But then these last 2 families are for, I believe, as far as I can tell, square lattice only. And then there's not a symmetric Trotter decomposition. So something to be aware of when you're working with them. And then I also wanted to note, we actually have a repository specifically for semi-supported Hamiltonians, which you can get from the QR code. And these are things that people worked on as projects in the past and are sharing with everyone. So there's an extended Hubbard model there, Pneumatic Dirac, and I'm certainly there should be others. I think I have plans to contribute as well. And so, yeah, if you can check them out, but you can also contribute your own Hamiltonians here too. All right, and that's it for.
Thank you. So other questions? Yes.
So I have a question regarding the fields. So you showed there are 4 fields.
Yes.
So where, I mean, is there a rule of thumb which I can use in choosing the fields? I mean, is it better for stabilization or errors or fast code? I mean, I don't know.
For continuous versus the discrete, mainly, I think that might be a question there. Yeah. So in the discrete, I think it's often the case that discrete will be more efficient, but there are cases where there are sampling issues where maybe somebody else has more experience with working with continuous fields. If anyone else wants to comment on that.
You want to comment?
Yeah. So somehow, if I can avoid continuous field, I will avoid them, because when you have continuous fields, you have to have some good update for the continuous fields, and then you come into, so I avoid them. That's all I can tell you by experience, because it becomes a bit complicated to update.
But then we have other features like Langevin and HFC.
Yeah, so that's it. So the code is so we have Langevin dynamics, and we have hybrid Monte Carlo with exact forces, which is implemented in the code. We have but that comes with a set of own problems, right? So I claim that Langevin dynamics does not work out of the box, and HMC does not necessarily also work out of the box. So you have to be a bit more careful. Whereas if you have single spin flip local fields, discrete fields, this is something which will normally work out of the box. In many cases you can't. Maybe some cases you have phonons and you can't integrate them out. So there are many cases where you do have global fields which are continuous, but you would like to avoid them. I don't know if somebody else has different experiences. There's no. Yeah. Also, there was a nice work with Maxime, who's not here now anymore, but there's something a bit weird, is that when you do global updates, you basically do the update and then measure. right? Whereas, and so when everything works fine, you have no fat tails, etc., then everything's fine. But normally it's more efficient to do a single spin flip and measure right after a local observable, right after the single spin flip. So single spin flip comes with less fluctuations. I was telling, yeah. We can talk about this for ages, right? So avoid continuous field if you can. I think that's a summary of what I had to say. Could have been much more efficient.
May I ask a question?
Go
Sure.
ahead.
The type T equals 4. You said you use the complex field, right?
That's right. Yes.
Did you that would cause the severe phase problem? Did you do the phase approximation or something else?
A phase problem? Are you thinking like a sign problem?
Yes, it's a phase problem. It lies the complex. It is not real. The weight is not real.
So one thing about these fields is we aren't using them actually as complex numbers. We have the real part and the imaginary part that we're using as two real fields. I just want to make sure you're clear on that.
Right. I know. The field is complex. But the weight may vary. The weight is also complex. This may cause. This is the phase problem.
You mean the sign problem?
Yeah. Right. It's the sign problem. It's another form of sign problem.
Yeah, so maybe I can comment on this. The field is defined as a complex variable, but it's not really used as a complex variable as far as I understand, but it's rather, maybe Fakir can tell me which one is which. The real part is the
Discrete.
Hubbard-Satonovich discrete field.
Wait, send him the box. Wait, fuck.
We didn't want to disturb you, right? It's a dangerous place here. Listen, the thing is the following. We needed more space for the fields, right? So basically, the ALF started with a discrete field, plus or minus 1, plus or minus 2. Then we decided that that was not enough, so we defined a real field, right? So that'd be continuous. And then we decided that was not enough. For an operator, we needed to have 2 reals, right? And we decided to put those 2 reals in a complex variable. That's the history. So this choice is somehow historical. I think. Would you agree? I think that's how it evolved. And then we abused the complex field to do what we want to do. And in the example, which is in the ALF, the real part of the complex field is for the phonon degrees of freedom, and the imaginary part is for the Hubbard-Satonovich, something like that. So there's no, and in that case, there is a phase problem, which is for the spin spirals. There is a phase problem but it's so mild that you can forget about it. Right?
Okay. Thank you.
So I mean, maybe if Emilie puts back the spin spirals thing, you will see that there is a square root. Did you not put the implementation? There is basically, when you do a Hubbard-Satonovich transformation of HQMC, there is a square root of 1 plus QB, right?
Right.
And if QB is smaller than 1, is smaller than minus 1, then this will go negative, and it will get square root of negative number. You get an I, and you get a small phase, but it's very, very small for the QB, for the parameters we use typically.
Okay. Is that an approximation?
There's no approximation. This is exact.
Okay.
This is the
So we
maybe
could handle, we have the reweighting built into the
Yeah.
code. Johannes will talk about the sign problem
Right.
tomorrow, but basically you have the average sign, which as your second observable.
so the ALF as it stands, there is a branch which Zihong Yu is doing, but the ALF as it stands has no constraint path, has no nodal structure constraints or anything. It's basically an exact method. right? And if there's a sign problem, then you confront the sign problem. There's no approximation which is made.
Okay. Okay.
If that's the question, I'm not 100% sure that was the question.
Yeah.
Thank you.
Are there more questions?
You mentioned the textbook. Could you repeat? I missed which the textbook was.
Yeah, well, so a couple of things. You can access it here at the QR code. That's all the links. But I can also just go back to the first slide that had.
I have a problem with QR codes.
Okay, well, here you go.
That is the name. Okay, perfect.
Yeah, so you can type this in to your web browser and you will be able to read
Thank you.
Bakker's book. Yeah.
Maybe we can put the link also on the Discord channel. All right. Are there more questions? Yes, Faka.
You see, there is also, if you can put the last line on the Hamiltonians, I mean, for the people who are interested online and here, we should, the hope, that's again, Jonas did a very nice way so here's the question, how do we extend the ALF library to a number of Hamiltonians, right? We cannot always augment the number of Hamiltonians and always write a documentation and every release update the documentation. We don't have the time, nor the energy, nor the interest. So when you say, for example, extended Hubbard model, we did that with Johannes, and basically extended Hubbard model is a model which will work with ALF 2.5. And in this extended Hubbard model, there's only the Hamiltonian, right? So you download it and it's automatically done. And you can basically then just type return somehow, something like that. In principle, in practice, maybe not. And then you have your extended Hubbard model that will work. And the idea is really hopefully that every one of you who uses ALF, at the end of the project, you provide the Hamiltonian, you upload it there. You have a minimal documentation, 2 pages, 1 page, and you make it available to the community and also to the referees. We've been talking about this for 3 years now, 2 years. And in 2 years, we managed to get 2 Hamiltonians. So it's not working so well, but we never give up. That's the point.
Thank you.
One thing is that everybody who wants to do a PhD.
Yeah, there are more questions. Maybe there's somebody. It's Jefferson who sent the link for the paper on the Zoom chat. So for those on the Zoom, you can check that out. Okay, so are there some comments additionally or questions? Okay, so if not, I would say we go to the coffee break.
Yes.
Sorry, Zoom people. Thanks again to Francesca and Emilie. And we meet again in half an hour.